So now I guess we're going to transition to a few talks that are a little more focused on the science application side, but very much in the same vein. And I'm going to try and this is, the material I'll be talking about is stuff that I've been very excited about on the science side, looking at problems in galaxy and star formation with new generations of simulations. But I'm going to try and, in the spirit of this workshop, focus it on some of the computational challenges. But you'll have to forgive the fact that I'm going to be very biased towards the work that I've been doing in collaboration with Dushan and many other people on this problem recently. So, of course, in galaxy formation, there are many unsolved problems, but perhaps the biggest is trying to figure out why star formation is so inefficient. And this is a very long-standing problem, and this is, one of the major motivations for why we're doing things like putting all these messy baryonic physics into simulations, as opposed to the cosmological questions that Anatoly told you about. But here we're not talking about precision. So if you take your simplest model of galaxy formation, where you put in gravity, you put in cooling, and you put in some rule for how gas turns into stars that you take from the observations, you predict a mass function that looks like this red line. You basically turn the universal baryon budget of every dark matter halo into stars to lowest order. And this black line is what's actually observed, and a more theory-friendly way of quantifying this is what's plotted here from Ben Moster's work. This is the ratio of stellar mass to halo mass in observed galaxies as a function of their halo mass. And this dashed line is what you'd get if you turned about 10% of the available baryons into stars. So I show this, it's probably familiar to many of you, just to highlight that there's really a orders of magnitude problem here that we don't really have a good answer to. Galaxy formation is not, a factor of 2 problem that we still have to figure out. It's a, this galaxy is 3 orders of magnitude less massive than our naive theoretical model predicts. So what do we think the explanation is? Well, hand-wavingly, there's been an idea around for a very long time, and many people have worked very hard on making it less hand-wavy in the last few decades. And the idea is that feedback from stars explains this downturn. So down here, you're talking about some tiny dwarf galaxy. The idea is it starts forming stars. Those stars start exploding. You get a few supernova explosions. It's a very shallow potential well, so that just throws out the gas. And that explains why, in the end, you turn so few of its baryons into stars. And more recently, people have started talking about maybe the role that supermassive black holes play on the high mass end of explaining this downturn on the other side. This peak in the middle is around the mass of the Milky Way. All right, so this idea has been around for 4 decades plus. So why isn't this a solved problem? Well, it turns out that doing this right is horribly complicated and involves a lot of physics that we don't really understand. So what are the ingredients that we need to be able to simulate this process? Well, we need initial conditions, but we've got Planck and WMAP. We've got a pretty decent initial condition. And then we need the physics. Well, okay, what's the physics? Gravity? Great. I mean, for all that we've just heard, at the level of a 3 order of magnitude discrepancy, we can do gravity. We might argue about, for precision cosmology, how that affects it, but solving gravity isn't that bad for this problem. Hydro and ideal MHD, great again. We can do that. We have good methods that we've tested that can do this. Chemistry and cooling physics of gases, well, we understand the chemistry. It's not terrible how we've implemented it. There are regimes that probably still need work, but again, it's well understood physics. The real problem is this feedback story that I mentioned, and that's where we just really don't know what we're doing very well, and also where there's a lot of computational challenges to make progress. So just to give you an idea, the sort of standard in most simulations has been to say that we're going to boil feedback down to the most violent things we see, supernovae, and we're just going to dump this canonical number of 10 to the 51 ergs into the ISM every time there's a supernova. And people have realized for a very long time that that alone doesn't work. You dump all that energy in, the problem is it just gets radiated away very efficiently. The cooling time of the gas in the ISM, especially if you can't resolve the phase structure in the ISM, is just too fast, and that energy gets radiated away. So what's typically been done is you sort of cheat at this stage and insert some subgrid approximation for the physics you think should be happening or the effects you think should be happening. And commonly that takes, in the current state of the art still, that commonly takes one of 2 forms. Either you just say, I'm going to still dump the energy in, but I'm just not going to let it cool for of order of galaxy dynamical time, and then it'll do something interesting. Or I'm just going to skip the question entirely and just force gas to flow out of my galaxy. I'm just going to kick particles at some very large velocity until they launch out of the galaxy. And you can tune then that to give you some reasonable star formation history. This is just one example from cosmological simulation by Piontek and Steinmetz. It's supposed to be a Milky Way-like galaxy with a basically flat star formation history. This black curve is what happens with there's no feedback. Everything just radiates its energy, collapses very quickly, turns into stars in basically a dynamical time, and you end up turning all your gas into stars. If you just do this energy dump and nothing else, you get the red line. It maybe slows things down a tiny bit at highest redshifts, but cooling catches up to you and ruins everything. So how can we do better? Well, again, I'll focus on what we've been working on, but many people in the community have been thinking very hard about this and trying to take advantage of improvements in computation and improvements in our understanding of the physics to model this more realistically. So this is sort of a state-of-the-art simulation I'm showing here of a single galaxy showing the multi-phase ISM. You've got cold molecular clouds in blue, pink is warm ionized gas, and yellow are sort of hot supernova bubbles. So what are the ingredients going into this simulation? Well, of course, we can take advantage of Moore's law and now go to much higher resolution than was possible even a few years ago. So it's now possible to simulate galaxies, even cosmologically, with resolution of order 1 to 10 parsecs, depending on the size of the galaxy. And we can put in these cooling physics that we think we understand. So when you start getting to this kind of mass and spatial resolution, it becomes meaningful to treat the cold gas in the galaxy. If your resolution is a kiloparsec, it doesn't have any physical meaning to assign gas very low temperatures because you can't resolve any structure with those kinds of temperatures. Now, it's still hopeless to resolve how stars actually form in these kinds of simulations. Mark will talk more about that, and there's a lot of open problems how we map between those. So we still have to have a subgrid scale, and I think what's really happened is we've been able to push on the galaxy side the subgrid scale down to the sort of GMC scale, while people on the star formation side have built up to the GMC scales. And there's I think, going forward, a real important point where we're going to make a lot of progress is mapping between those communities, not just scales. But then once stars form, the challenge here is not just to put in these different pieces of physics, but also to computationally understand how these very small scales couple back onto very large scales. And that's really part of the challenge. So there's a lot of different physics that happen when stars evolve. It's not just a thermal energy dump of 10 to the 51 ergs per supernovae. You can take your favorite stellar evolution code and just take even just the biggest things that we know should be happening. There's supernovae, sure. There's type 1As, there's type 2s. Supernovae have not just thermal energy, but they have mass, they have momentum, they have kinetic energy, they have metals that they carry, and you should follow all of that. There's also stellar winds happening continuously from all your stellar populations, both young and old, and we want to follow that. But there's also radiative feedback, so you really should be following things like photoionization and photoelectric heating. It's easy to forget from the galactic side, but there's 100 times more energy in photons than there is in supernovae from a stellar population. It's not a good approximation to drop those terms. And this is just making the point. If you just look at, for example, the momentum flux in just these simplified list of mechanisms, say radiation pressure, photons scattering off of gas and dust, supernovae and stellar winds, their sort of initial bulk momentum, it actually turns out that all three of these numbers are basically comparable. They operate over different time scales, sure, but this is just one of many ways of saying that these are all comparably important, and it's not, it turns out, a great approximation to drop any of these terms. And then, of course, there's all these other physics that we know are happening that we usually just gloss over. So this is an example of a cosmological simulation run with the best attempt to put these physics in, but in the spirit of this meeting, I want to emphasize that there's a lot of still uncertainties in how you implement this. I just said radiation, but we don't have good radiative hydrodynamic algorithms that can be used on the fly in these kinds of simulations. We have a lot of people working on it, and we have approximations that work well in different regimes, but we don't have one thing that works under all conditions. So sorry, I should have explained. This is a Milky Way mass galaxy in formation. This is a mock optical UGR image of the stars, and this is the gas. The green is the warm ionized gas. The magenta is cold atomic and molecular gas, sort of 1,000 Kelvin and below. and the red is hot gas at 1,000,000 Kelvin and above. And you're seeing a physical couple hundred kpc box on a side. So you can see the really violent and dramatic role that feedback has on shaping the evolution of this galaxy. That's sort of the last giant starburst episode this thing has. It blew out a big super wind. And now it starts to finally settle down into something that sort of looks more like a calm galaxy that we're used to seeing. But especially in the early phases of evolution, this thing is very strongly dominated by things like strong outflows, et cetera. So here's the branding for this, the advertisement. This is this FIRE project, Feedback in Realistic Environments, which I've collaborated with Dushan and Claude Fauché-Giguère and Elliot Quarterdon, and there's a number of papers in preparation on this. I'll skip this, and again, I don't want to get too much into the science side. I want to show just one example, though, of why you really care about putting all these physics together and why we still need to be thinking about the physics that might still be missing. So you can quantify from different simulations, and it's not important what these are, how the outflow rate from the galaxy scales as a function of the star formation rate. So this is just mass in outflow over mass in stars, some mass loading of the winds. The black line is what happens when you turn everything on. The red line is what happens if I remove the radiative feedback mechanisms. Okay, the wind outflow rates go down. The blue line is what happens if I remove supernovae and stellar winds. Okay, the outflow rates go down, not surprising. But what I want you to see, again, since I want to focus on the sort of guts of this, is these two lines should, if these processes were really separable, sum to significantly more than the black line. Because I'm double counting some feedback mechanisms, and I've just turned off one mechanism here and one here. But they don't. They actually, this is a logarithmic axis, they sum to significantly less than the black line. There's very strong, very nonlinear couplings between different feedback processes. Radiation pressure and photoionization change the medium into which supernovae propagate, and that changes all the subsequent solution. So I say that to partly caution that you shouldn't take these as a final value because there's still physics missing, which could itself also strongly nonlinearly couple to these processes. That said, you can start to get, with these kinds of simulations, some encouraging results. So this is one initial result. When you put all of this stellar feedback physics in, you start to get stellar masses as a function of halo mass that look reasonable. These dashed lines are what's observed, and these points are this generation of simulations. And the last thing I want to say is that, fortunately, I think we're in the limit for this problem where we're really physics limited rather than numerical errors limited. So there's been a lot of discussion in the literature about, for example, can SPH do anything, basically. I'm poking fun at my collaborators on the Arepo team here in particular. And there are certainly problems. I mean, this is supposed to be a Kelvin-Helmholtz instability, and you can see what Gadget 2 does with it over here. It just doesn't work. Now, that particular problem is a fixable one. I'm not saying that every issue with SPH is solved. It's certainly not. That particular problem can be solved, and you can compare a method that does well on these contact discontinuity instabilities to one that doesn't. And here's what you get in terms of the stellar mass to halo mass ratio from these cosmological simulations by using, for example, those two codes and many other numerical variants. So basically here, this black point and, for example, this green point use two completely different numerical SPH methods that do wildly different on all the fluid mixing test problems. And you get, a 10, 20% difference in the stellar mass. It can be bigger for some of the numerical variants. It can be a factor of 2 or 3, which is certainly cause for concern and good motivation to work harder. But compare that numerical difference to here's what happens if I just yank out one of the feedback mechanisms, the physics that I'm putting in this code. If I take out, say, photoionization heating or supernova explosions and just delete that from my simulation, I get orders of magnitude changes. So the good news, in a sense, is that we're physics limited rather than numerically limited. The bad news is that we're physics limited and we don't understand the physics that we're missing. So I'll just leave this up, my highlighting of some of the challenges in these particular types of simulations. I mentioned feedback. I mentioned the fact that we don't know all the physics and that there's still open problems in putting in the radiation transport. And Mark will mention this more, I'm sure, that there's also a dynamic range problem that makes parallelization very, very difficult for these kinds of problems. And I should also mention, just because it hasn't come up that because you're in a cosmological simulation in particular, you're integrating for a crazy number of dynamical times for the material in the center of a galaxy. Much more than we're used to for a lot of the test problems that we use these codes for. And that means that you need an extremely stable, robust method. And sometimes it can actually be more important that your method has good conservation properties than has sort of formal, certain formal accuracy properties. But it's a very difficult thing to assess the balance between those sort of ahead of time. So anyways, I'll leave there.